Here we have a table of standard reduction potentials, and this is a shortened version, but you can see on the left side we have different half reactions, and all of these half reactions are written as reduction half reactions. Remember, gain of electrons is reduction. So if we look at our first half reaction, we have silver ion gaining an electron to form solid silver. That's a reduction half reaction. And the standard reduction potential turns out to be positive 0.80 volts. And that's compared to this half reaction down here, which corresponds to the standard hydrogen electrode, which is the reference value. So this has a potential of 0 volts. And so all of our other half reactions are compared to this one. The more positive the value is for the standard reduction potential, the more likely the substance is to be reduced. So let's compare the reduction of copper 2+ ions to the reduction of zinc 2+ ions. Let's compare these two half reactions. So if we are reducing copper 2+ to solid copper, the standard reduction potential is positive 0.34 volts. And if we are reducing zinc 2+ to solid zinc, the standard reduction potential turns out to be negative 0.76 volts. The more positive value, the more likely the substance is to be reduced. So obviously positive 0.34 is more positive than negative 0.76. So we know that this must be the reduction half reaction. So if we're talking about a redox reaction involving copper and zinc, this must be our reduction half reaction. So let's go ahead and write that. This is our reduction half reaction where we have copper 2+ ions gaining 2 electrons to turn into solid copper. And the standard reduction potential is positive 0.34 volts. So this is equal to positive 0.34 volts. Well, we know in a redox reaction something is reduced and something is oxidized. And since we already have our reduction half reaction, we need an oxidation half reaction. That must mean that this should be our oxidation half reaction. But here we have it written as a reduction half reaction. So we need to reverse this reaction to show it as an oxidation. We need to start with solid zinc on the left side. So we start with solid zinc on the left side. And zinc is oxidized into zinc 2+ ions, and we're losing 2 electrons. So remember, loss of electrons is oxidation. So now this is an oxidation half reaction. So we need to find the standard oxidation potential for this half reaction. And we can do that by looking at our table here. So negative 0.76 is the standard reduction potential. So since we reversed our half reaction, we just need to change the sign. So the oxidation potential must be positive 0.76. So all we need to do is reverse the sign to get our standard oxidation potential. So we get positive 0.76. To find our overall redox reaction, we just need to add together our two half reactions. So to find our overall redox reaction here, we add the reduction half reaction and the oxidation half reaction. So these electrons would cancel out, and on the left side, we would get copper 2+ ions. So this would be copper 2+ ions and solid zinc. And on the right side, for our products, we would get solid copper and zinc 2+ ions in solution. So we get solid copper and zinc 2+ ions. This overall redox reaction should look very familiar to you because this is the spontaneous redox reaction that we've talked about in the last several videos as our example of a voltaic cell. All right, so we know this is a spontaneous reaction. And how do we find the potential for the cell? All right, so how do we find the standard cell potential? How do we find the potential for the entire cell? Well, to find the overall reaction, we added together our reduction half reaction and our oxidation half reaction. So that gave us our overall reaction. So to find our standard cell potential, we just need to add together our reduction potential for the half reaction and the oxidation potential for the oxidation half reaction. So to find the potential for the cell, we add the reduction potential and the oxidation potential. And so we get, when we do that, we're going to get positive 0.34 volts is the potential for the reduction half reaction, and positive 0.76 volts is the potential for the oxidation half reaction. So that gives us our standard cell potential. So for our cell, the potential is equal to positive 1.10 volts, which we already know this from previous videos, right? I talked about the fact that you can use a voltmeter to measure the potential difference, to measure the voltage of a voltaic cell. And you're going to get positive 1.10 volts under standard conditions. And so that's one of the nice things about the standard reduction potential table. We can calculate the voltage of our voltaic cells this way. Let's look in more detail at our half reactions. So let's start with the oxidation half reaction. We know that zinc is being oxidized, right? Zinc is losing 2 electrons. And those 2 electrons that zinc loses are the same 2 electrons that cause the reduction of copper. So zinc is the agent for the reduction of copper. So we say that zinc is the reducing agent. And sometimes students find this confusing because zinc is being oxidized. So why is it the reducing agent? Well, zinc is the agent for the reduction of something else, in this case, copper 2+ ions. So zinc is the reducing agent. Copper 2+ is gaining those 2 electrons. So copper 2+ is being reduced. But because copper 2+ is gaining those 2 electrons, it allows zinc to be oxidized. So copper 2+ is the agent for the oxidation of zinc. So copper 2+ is our oxidizing agent for our redox reaction. So let's look at our standard reduction potential table, and let's see if that can help us understand oxidizing agents and reducing agents. Well, we've been comparing these 2 half reactions, right? So these 2 half reactions right here. So let's compare copper 2+ ions to zinc 2+ ions. Right? Well, copper 2+ we know is more easily reduced, right? It has the more positive value, I should say, for the standard reduction potential. So copper 2+ is more easily reduced, and therefore copper 2+ is a stronger oxidizing agent than zinc 2+. So as you go up on your standard reduction potential, right, you're increasing in the tendency for something to be reduced. And therefore, you're increasing the strength as an oxidizing agent. So as you move up on your standard reduction potential, increased strength as an oxidizing agent. So copper 2+ is a stronger oxidizing agent than zinc 2+. All right, let's think about the opposite. So as you move down on your reduction potential, so as you move down here, so let's compare solid copper and solid zinc, right? We know that solid zinc was our reducing agent in our reaction. And that's because the reduction potential was the more negative one. So that means this is more likely to be the oxidation half reaction. So as you move down on your reduction potential, right, you have an increasing tendency to be oxidized. So therefore, you have an increasing strength as a reducing agent. So zinc, right, is a stronger reducing agent than copper because, again, looking at the reduction potentials, you know that it's more likely to be oxidized. So going down on your reduction potentials, increased tendency to be oxidized, therefore increased strength as a reducing agent. So if you look at lithium, right, so lithium here, lithium is even more negative for the reduction potential. Therefore, this is even more likely to be an oxidation half reaction. So lithium is a stronger reducing agent than zinc.